Hello everybody, and welcome to my talk on the topic of transmission Raman spectroscopy of inner layers, chemical analysis of fresh produce. My name is Rani Arielly. I'm from the Institute of Agricultural Engineering, the Agricultural Research Organization at the Volcani Center, Dagan, Israel. I want to start by talking to you about elongating produce lifespan. These days, we require year-long supply of every type of produce. And because we want to achieve this, we need to store them for longer periods, because sometimes not every type of produce is grown every season. In addition, because we want to export our produce, there is an increase in sea freight, which is under cooling condition and takes long months. All of these cause more frequent damages to the produce, and some of these damages are visually undetectable. This may be inner rot, or maybe some off flavor that is discovered only when you taste the produce. And all of these, they deter the customer from buying the produce, and even causes the people involved in the supply chain to dispose of the produce at some point, and all of these cause financial losses. So in order to address these issues, we need to conduct analysis of the inner layers of the produce, especially produce that is sized several centimeters. Now, currently, the common methods for doing analysis of this type of produce and others is, first of all, destroying it, extracting all the content, and then using a chromatography step followed by mass spectroscopy or NMR or IR or near IR. Now, the disadvantage is first of all, that you destroy your sample, you can't use it later, and also the sample preparation time tends to be long, and if you don't destroy the sample, you only sense the surface, maybe you will have low resolution, or the data won't be good enough to be meaningful. Now, we want to penetrate the sample without destroying it. That means that we need a probe that interacts with low probability. Now, if we think of the contents of our produce, and the most of it is water, maybe because water is transparent in the visible and near visible areas, maybe we can find some optical windows that have better transmissibility, and then we can use these optical windows in order to conduct our research. So the methods I'm suggesting is using Raman spectroscopy in transmission mode. Now, the advantages are that if we successfully locate this optical window, we can directly interact with the point of interest, which is the inner tissues of our produce, and we can get plenty of useful information, because the modes that will be present in our Raman spectra will be the basic modes mostly, and not some harmonics or combination bands. Now, there are disadvantages, some of which are the low cross section of the Raman process. Another is that there is no chromatography step, which makes the results more complex, and another one, that many popular excitation wavelengths are prone to fluorescence, which gives a strong background, which sometimes is a problem but maybe with modern analyzing methods it won't be. So now we need to locate the optimal wavelength to conduct our Raman experiment. And if we remember the previous slide, we saw the wavelength that water is transparent. But now we need to think of this more complex product with all its components and find its optical window. So in order to find the optimal wavelength to conduct my Raman measurement, I need to conduct a measurement of the optical attenuation coefficient. And I need to do it because there is a lack of publicly published wide spectral range attenuation coefficient measurements of products or its components. Now I can do this using a visible to near infrared spectrometer and a quartz tungsten halogen source that I have, and measure with these instruments slices of apple, in this case, of varying thicknesses, and then I can use the Beer-Lambert law in order to calculate the attenuation coefficient. Now you can see here in these graphs the measurement of the intensity as a function of thickness, and from the slope of these graphs I calculated the attenuation coefficient as a function of wavelength. And you can see that the best wavelength for transmitting radiation is around 800 nanometers in this case. At this point, I want to talk about the design of our Raman spectrometer. Specifically, what will be the needed laser power in order to get a decent signal-to-noise ratio? What will be the limit for that laser power in order not to burn our samples? And how can we improve on the common resolutions that I found in off-the-shelf spectrometers that I used in the field and in the lab as well? And our design, you can see it in the schematic. We have a laser source. Its beam is expanded in order not to burn the fruit, and it passes the fruit and then focused back into the monochromator, which separates the wavelength and inputs them into two cameras, one for the UV visible range and the other one is for the SWIR range. Now, our hope or our design is that by choosing the right focal length and the gratings and the pixel count of the cameras, we can reach a 3-wave number resolution of our Raman spectra, which should be good enough to finally resolve almost all of the peaks that are in the measurements. In order to calculate the needed laser power for getting a decent quality Raman measurement, we have to take into account the loss of the monochromator, the quantum efficiency of the detector, and also its dark current. We have to take into account the fourth power dependence on the wavelength of the Raman cross section. And if we take these into account and require some decent signal-to-noise ratio and consider the dependence of the power on the intensity of the radiation that passes through some point, the density of the material at that point, and the cross section of the Raman, we can achieve, by also considering the geometric dispersion of the radiation, the needed laser power. Now we consider a calculated result, and we can see that the lowest needed laser power is somewhat below 600 nanometers. It's tens of milliwatts, but let's remember that this wavelength range is also prone to fluorescence, so maybe we would like to select some different wavelengths, so we will see about that. We also have to calculate the top limit for our laser power, which should be above the needed laser power for a decent SNR that we calculated earlier. Now we estimate this laser power using a simplified 1D calculation of the thermal conductivity, and we consider a water-based medium, which should be correct. Most of our content is water, and we consider a 50 Kelvin temperature increase, which should be safe and also useful in case there are some unwanted things on the shell of the produce. Now we consider broadening our laser beam to 2 inch, which is standard with optical component, and we consider a thermal conduction length of about 6 centimeters. Now, using this formula and all of these numbers, we calculate a maximum power of our laser of 1 watt. Now, this is an estimate, and we can take something even larger and use some filter in order to decrease the power if we need it, but this is the order of magnitude. Now, after we've seen different aspects of our Raman system design, let's talk about how we analyze the data. Because since we don't have a chromatography step, we measure all of the chemical components together, and we need to have some algorithm that will allow us to separate them and focus on what interests us. And we can see an example here at the bottom of a sample which is totally dominated by water, and only after when we subtract the water component, we can see all of those small details that may interest us. So our method is to use a combination of synthetic and real data. Most of the data is synthetic in order to train a convolutional neural network, and then use transfer learning using the real data in order to fine-tune the system in order to be successful analyzing our data. Now, we use a bank of like 300,000 samples, and we at the moment achieved accuracy of about 90%, but we need to investigate more topologies in order to fine-tune it and get higher results. So to summarize, we're trying to address the lifespan problem of produce, and we try to address it using transmission Raman spectroscopy. We've talked about different aspects of the system design and how it can be optimized, and we've shown how we approach the data analysis using synthetic data and neural networks. Some future steps that we wish to accomplish: we want to improve the spectral range and measurements accuracy of the attenuation coefficients. We want to do further research on convolutional neural network topologies and reach a near 100% accuracy if possible. Then we want to build and demonstrate our design and prove strong correlation with controllable and destructively analyzed samples. We want to take samples and do something to them that we know what we did, and then measure the effect using chromatography and mass spectrum, all of the usual methods. And with that, I thank you for your attention, and if you have any question, I'll be very happy to discuss them. Thank you very much. Have a nice evening.